Hi, my name is Alexandre Curaudeau, and I'm a senior in the Aerospace Engineering Department. This summer, I'm continuing my research that I started last semester with the guidance of Professor Ian Boyd and Dr. Alexandre Martin on the LeMANS program. LeMANS is a CFD program specifically designed to model vehicles in hypersonic flows. Now, hypersonic flows actually pose an interesting problem in that at those speeds, the temperature gradients at the walls of the vehicles are actually high enough to change the chemical composition of the atmosphere surrounding the vehicle. So what we need to do is we need to develop a program that actually recalculates the new chemical composition at each instant in time and then substitutes those values back into our solver so that we can get our typical values that we use, such as pressure, temperature, density, and velocity. Now, my specific role is actually to determine or make sure that the program works as it should, and then to verify that the results that we're getting match results that we have seen in other experiments. So the first step in verifying a software is to make sure that all of the options actually work as intended by the designer, and to make sure that they all work together. Next, it's also important to make sure that you understand the errors in your program and to better understand the limitations of your software. Finally, it's important to pick a number of experiments that have been conducted that you can then resimulate in your program and compare the results. So the first step is actually to make sure that your options not only work by themselves, but also together. It is possible that some of the options in your program might actually negate other options, thereby creating some problems in your initial setups. Then you want to make sure that all of your physical laws are actually properly conserved. This might seem like a simple thing, but it's an important thing to check, especially if some of your physical laws are more complicated. Finally, it's important to understand all the errors attributed with your results. There's both computer errors and physical errors that you have to look out for. In terms of computer errors, you typically look out for your rounding errors and then your convergence errors, which are more attributed to the type of numerical solver that you choose. Your physical errors, on the other hand, deal more with the actual physical model of the vehicle that you're using in your simulation, and then the inaccuracies in the flow properties that you're using in your initial setup. So validation is important because you need to make sure that your results that you're getting are actually what you would see in the real world. So what you want to do is pick a number of experiments to which you have access to that you can try to resimulate. Now, an important step in this is also to make sure that your mesh that you're using for your object is actually refined enough so that your solution becomes independent of your mesh. Failure to do so could actually yield inaccurate results. So the first step in validating a software is actually to pick experiments that you can resimulate. Now, you need to have enough information to both recreate the test object and to also recreate the flow parameters. This isn't always easy, as you'll find out, because you'll actually be limited in terms of the amount of information that you'll have access to. Finally, you'll want to make sure that you refine your mesh for the reasons that we discussed previously. Here we see a typical example of an experiment that we used to help validate our software. You can see that the amount of information provided is actually quite limited. So what you have to do is actually, from this information, try to get as many other flow parameters as possible to give you a complete flow parameter initial setup. As you can see, the actual solution provided by NASA is actually quite unrefined, and we suspected that they did not have enough time to refine their mesh as much as possible. You can see on the right that the mesh that we provided is actually a lot more refined in the shock area to address the issue that we found in NASA's solution. And as you can see in our solution below that mesh, we were able to actually solve that problem. What you'll do throughout your project is actually validate your case or your program for more than one type of example, such as either outer flow problems or inner flow problems, such as internal combustion engines, and so on. Everything depends really on the different ways that your program can be used. I hope that you've enjoyed this presentation, and thank you very much.